Okay, good. Okay, so let us start. And last time we discussed the a very interesting relation between the analytic structure of complex function on the complex plane and its topological property. So essentially, I remind you what we did. We discussed a function that was analytic in the complex plane, and so it's a complex plane. There's a contour C on the complex plane, and we had this function that said it was a function f of z that was analytic everywhere except maybe a finite number of special points that are poles of this function. And in addition, this function had also a finite number of special points where its function vanished, and these points are called zeros of the function. And then we established an interesting relation that says that the number of poles minus, sorry, I take it back, number of zeros inside the domain C, inside the, oh, and actually, sorry, I take it back even here. I was not careful enough. So it's a counterclockwise contour C. So, and the function has a finite number of zeros inside this contour minus number of poles. So this thing is actually equal to 1 over 2 pi times the change of the argument of the function f of z computed along the contour C. So what it meant that I take the contour C, I perform one loop along this contour and compute the change of the argument of the function f of z, and this will be precisely equal to the number of zeros of this function inside this contour minus the number of poles. So this was a reminder. This was a reminder of this theorem that we discussed last time. And today we're gonna build on this relation, and the next thing that I'm like to describe, it's called Roche Theorem. I probably mispronounced it. It's a French name. So if there are French-speaking people in the audience, you can correct me. But so how you should pronounce it? But it's something like Roche's theorem, and this theorem states the following. So suppose there is a function f of z in the complex plane and another function g of z, and both functions are analytic function within a simple closed contour C on the complex plane. So it's the same picture like the one we had last time. So there's a contour C on the complex plane, But this time there are two functions, f and z, that are analytic on the complex plane. And again, both functions may have special points like poles and zeros. And then there is an additional condition to it, which was not there when we discussed the last theorem. And the special condition says, suppose that function f of z, absolute value, so this is a function f of z, is greater than the function g of z, absolute value, everywhere on C. And then the theorem states that then f of z and f of z plus g of z have the same number of zeros inside C. So just to give you an example, imagine that example. So imagine that we have contour C, which is a unit circle. So 1, minus 1, I, and minus I. This is an example of C. And let us imagine that we have two functions such that function f of z, such that they both analytic, but f of z as an absolute value is greater than g of z. Can anyone give me an example of such functions?
What we are doing now, Dima?
Sorry?
What we are doing now? Can you repeat?
I'm asking to give me an example of these functions that satisfy the conditions of this theorem, just to be sure that we understand what are we talking about.
that the absolute value of f של z, f of z will be greater than g of z?
Correct. That's a necessary condition, and they both need to be analytic.
Okay.
So can you give me an example of such functions?
I don't know, z and z plus 1.
Okay, let's see. So z and z plus 1. So who will be greater?
Plus 1.
So you think that z plus 1 absolute value will be always greater than z on the unit circle.
I'm not sure.
So what is the value of the function? What is the value of the function g of z on the unit circle? What is the absolute value of z on the unit circle?
Always 1.
Always 1. So this is always 1. What is the value of the function z plus 1 on the unit circle? What is the maximal value and what is the minimal value? What is the greatest possible value the function z plus 1 takes on the unit circle?
2.
2. Correct.
Zero.
So the maximal value of z plus 1 is 2. What is the minimal value of z plus 1 on the unit circle?
1.
0, no?
0. So is 0 greater than 1?
No.
No. So the function z and z plus 1 do not satisfy the condition of this theorem. Can you give me another example?
So z plus 10.
Okay, good. Z plus 10. So is z plus 10 greater than the absolute value of z?
Yes.
Good. So because this z plus 10 is greater than 9, is always greater than 9, and 9 is always greater than 1. So these two functions satisfy this condition. And now what would be the statement? What would be the statement of this theorem if we focus specifically on these two functions? What this theorem will tell us? What Roche theorem will tell us? Let's specify the Roche theorem for these two functions in equation. If you will specify this condition, that it means that you understood what the theorem is about. G of z. So what the theorem says. That's a condition. Okay, so now let's go again and try to recall what the theorem says. So if this condition is satisfied, then what must happen?
Same number of zeros.
So who must have the same number of zeros?
F of z plus g of z.
So in this case,
2z plus
function f plus g will be equal to z plus 10, must have the same number of zeros as what function? F, correct. So let's count how many zeros they have. How many zeros the function z plus 10 has inside unit circle?
0.
None, correct. How many zeros function 2z plus 10 has inside the unit circle? 0, correct. So it satisfies the Roche theorem. However, this satisfies in kind of a very, very trivial way. 0 is equal to 0. Let us try to find another example of two functions f and g such that f. So this was a trivial example, somewhat trivial example. Because the number of 0, this has 0, 0, no zeros inside unit circle. And so this function. Do you understand this example? Okay, can we invent a function which is more complicated such that Roche theorem is satisfied and count zeros? Z plus
Z plus A to the n.
plus 8.
Plus A.
Z plus A to the n. Yeah, but let's choose a specific A.
For the unit circle.
Yeah, I think if it's only linear functions, it will be always trivial. Let's pick something which is not linear.
Maybe 1 over z squared. And,
1 over z square. Okay, let's try this. 1 over z square is not greater than g of z on the unit circle because they both have a 0 absolute value 1.
yeah, we have to change the g of z.
Nonlinear equation. So, you want something like cosine.
Let's try something simple. Let's take a times z square, and let's choose a to be 2. Okay, that's let us check that f of z is greater than g of z. Is f of z absolute value greater than g of z? What is the absolute value of f?
Two. No.
Correct. What is the absolute value of g?
1.
Is 2 larger than 1?
Yes.
Good. Okay. Then we're in business. I'm thinking about, is it a phone or Skype? Well, it's our secretary. Let me answer. I'm sorry. It will be easier because she will. Shalom. Shalom. Well, okay, sorry. She will probably call again. I apologize, but okay. So 2 is greater than 1. That's good. So these two functions satisfy the condition. Hopefully, it's less trivial than the previous example. So what shall we do? Let's check what is the function f plus g. How the function f plus g looks like in this case.
2z squared plus z.
2z squared plus z. And supposedly, it must have the same number of zeros as a function f, which is 2z squared. So the number of zeros inside unit circle has not changed. So let's explore the zeros of this function. So where f plus g is equal to 0? So okay, so one point is z equals 0, and another point is 2z plus 1 is equal to 0. So z equal minus half. So there are 2 points, one at 0 and another at minus 1/2. Both lie inside the unit circle where this function vanishes. So 2 zeros both lie inside the unit circle. How many zeros function f equal to 2z squared has? 2. Where do they lie?
Both in z zero.
both in zero. So it has a zero of the order 2 of the degree 2. Both functions have the same number of zeros inside unit circle, as we have expected from the Roche theorem. Any questions about Roche theorem? Okay, so now let's try to prove this theorem. I think the proof is elegant. So let's assume that functions are analytic, as we assumed inside C, and have no poles in it, only zeros. So we have assumed that there are no poles inside C. So if the function have no poles, then our famous theorem from the last lecture that says number of zeros minus number of poles equal to 1 over 2 pi change along the contour C of the argument of the function f of z plus g of z simplifies. So if the function f and g have no pole, how can I simplify this statement?
Number of zeros equals
Correct. So it just says that the number of zeros is equal to 1 over 2 pi delta C argument, the change of the argument along this line. Or, so let me put here f plus g to denote that it belongs to the function f plus g. Or the same can be written as 1 over 2 pi I change along the contour C of the logarithm of the function f of z plus g of z. But now let me write this logarithm as 1 over 2 pi I change of, and here inside the logarithm I write f of z times 1 plus g of z divided by f of z. So I just opened brackets here and wrote the argument of logarithm as a product of two terms f and 1 plus g of f. Did you follow the logic?
separating the lines.
I'm separate. But now look, what is the function, how the function 1 plus g over z over fz looks like? Does this function has any zero poles inside contour C?
Wherever f of z equals 0.
I'm going along the contour C right now. The function f is not allowed to have any zeros on the contour C. So what can we say about this thing which is 1 plus g over f?
It has no zeros.
It has no zeros. It has no zeros because f is always greater than g. Therefore, this thing is strictly greater than 0. And therefore, I'm allowed to write this as a logarithm of 1 to pi I dc logarithm of f of z plus 1 over 2 pi I dc logarithm of 1 plus g of z over f of z. But what is the value of the second term?
Always positive.
So what it means about the change of the logarithm of the closed curve?
So delta C.
Yes.
It has to be positive as well.
Or you mean that it's imaginary? Because you're 1/200.
So what is this thing? So you have a contour C. It's a closed contour. And you compute the change of the logarithm on this line, on the closed line, assuming that the function inside the logarithm always positive. What would be the change? No. What function do you have in mind when you got 2 pi? So again, so this is the plane Z. There is a closed contour on the plane Z. Inside the logarithm, you have a function which is 1 plus g over f of z. How does this function look like?
And the opposite of
How many times it encompasses the zero? How many times it encompasses the origin? It doesn't. So if there is a function that does not encompasses the origin, what is the change of its argument on the closed contour? It's zero. So this thing is zero. And therefore the entire thing is equal to 1 over 2 pi I dc logarithm of f of z. So what we have shown and what we have started with, we started with the number of zeros of the function f plus g. And we found that it's equal to the change of the logarithm of the function f of z. But this thing by construction was equal to the number of zero of the function f. Okay, so if you want a pictorial representation of this thing, so there is a contour C in the complex plane, and there is its image, and its image of this contour by functions f, g, and f plus g. So if there is a point, so we follow the point z as it moves on the contour C in the plane of z. So its image will be function f of z. The image of the point of the function g of z will be this, such that altogether, this is the image of this point under the function f plus g. And now what we count is how many times this thing encompasses zero, because this will be by construction the number of zeros of the point of f of g. And we under condition that this, the value of this vector is always greater than the value of this vector. So if you want to have an artistic image, it's called the dog on the leash. So imagine that the owner, an owner is f, goes around the pole, which is in the origin, and has a leash, and has a dog on the leash. So if the leash is very short, shorter than the distance between the owner and the pole, then the dog cannot wind around the pole, because the owner is always at the distance such that the dog cannot wind around the pole. Therefore, the number of times the dog winds around the pole is the same number as its owner winds around the pole. This means that the leash is short. Leash is short as g of z is shorter than the distance from the pole. Now, if you have a dog on the long leash and you walk around the pole, that God only knows how many times dog can run around the pole. So this is what this theorem tells. If you have function f plus g and f is much greater than g, then the number of times the function f plus g circles around the pole, it's the same number of times the function f circles around the pole. Now, why this theorem is so important? Because it allows to establish many interesting results. For example, the fundamental theory of algebra. Theorem of algebra follows from this theorem. So who knows what is the fundamental theorem of algebra? Well, I can tell you that it has to do with the number of roots of polynomials. And this is very important theorem in the algebra, and it's connected to the complex analysis. So what do we know about the number of roots of a polynomial of a degree n? Any polynomial of a degree n, how many roots does it have?
N.
It has n roots, provided that the roots are in the complex plane. So if you're searching for roots on the complex plane, that any polynomial of a degree n has n roots. So if you have a polynomial of a degree n, which schematically looks like that, it must have n roots on the complex plane. So it has points they call roots, z1, z2, zn, such that Pn of z1 is equal to Pn of z2, so on, Pn of zn, and it's equal to 0. How can we prove this theorem based on Roche theorem in one line? Say it again.
Z1 and Z2 are the roots of the polynomial?
Yes, correct. So it must be n points. Some of them may be identical. In this case, they count as many points as their identical roots.
אז אם משהו מקיים את התיאוריה של רושה, אז הוא מקיים את זה בעצם.
Okay, so what function should we choose as function f and g?
עכשיו, כמו שבחרנו קודם.
F of z and g of z. So what function would you choose?
כלליות או משהו ספציפי?
To prove this theorem.
אפשר מה שהשתמשנו בו קודם. 2z בריבוע ועוד z ו-z.
But how does it help to prove anything which is absolutely general for any polynomial of the degree?
Dn minus 1.
Z n
Dn minus
and how does it help us to prove this?
1. What?
How does it allow to prove us the fundamental theorem for algebra? So what is the contour that you want to choose? By the unit circle. By the unit circle.
What?
I don't understand the problem. If the Z1, Z2, and so on are the roots of the polynomial, doesn't that by definition mean that n of, if you plug in Z1, Z2, and so on, you get 0?
Yeah, but you need to show that such points exist and there are n such points. How do you know that there's n points that are roots of these polynomials? Why not n plus 1? Why not n plus 2? Why not n minus 1 or n minus 2? So the equation is, how do you show there are precisely n points where this function vanishes?
Well, I usually factor out. You factor out a Z.
So let us be specific. Let's take a polynomial of, I don't know, of degree 2. Example. Let's consider a polynomial of degree 2, which looks like a2z squared plus a1z plus a0. I know there are two roots, and I know it because I have an explicit solution for this. I learned it at school. But suppose I don't know the explicit solution. How can I prove that there are only two roots? Using Roche theorem.
Because if this is larger,
Who is larger?
A2 of z squared
A2z squared is larger than what?
is larger than the remainder.
A1z plus a0, provided that the circle C is what? is very large. So if I take, it's clear that this grows quadratically.
As R goes.
So this scales as r in the power 2, this scales as r equal the power 1. So I can always choose a circle that is so big that this term is bigger than that term in absolute value. Okay, so we are choosing a very big circle. And then we know then this thing, the first term, is always larger than the rest of the polynomial together. So what it means that the number of zeros of the entire polynomial P2 is the same as the number of zero as the first term of this polynomial, A2 times Z squared. How many zeros the term A2Z squared has? Correct. Is equal to 2, and they both lie in the origin. Therefore, this polynomial P2 has 2 zeros inside a very big circle. Did you understand the proof for the polynomial of the degree 2? So what happens now if the polynomials of degree n? What do I choose?
A and C of n.
Then-
Greater than the remainder of the polynomial.
Then I choose a n z n, and this will be always greater than everything else. And then I say how many zeros the function a n times z in the power n has.
And roots.
It has n roots. It vanishes n time at the origin. And then by construction, by Roche theorem, the entire thing has to vanish the same number of times within this contour, within this circle of a very large radius. I can even establish where the roots of the polynomial must lie, because the region and the complex plane where the roots must lie are actually determined precisely by the condition that f of z is greater than g of z. So if you're giving me a specific polynomial with specific coefficients, I can check where in the complex plane this condition is satisfied, and then I can tell in what region of the complex plane the roots of this equation must be. Do you want to have an example of this?
What if you need to integrate it in a smaller region than the big ball? Then the number of zeros change.
Yeah, but I may say that all zeros lie within all n zeros of these polynomials lie within the circle of some radius.
Yeah.
And if you give me a polynomial, I can be able to establish a condition where the zeros must be. So let's play with it a little bit. Let's take some simple polynomial and see where the zeros of this thing must be. Okay, so let me take a specific polynomial P of z of degree 4, which is z in the power 4 plus z in the power 2 plus 1. Let's try to use this theorem and establish where the zeros. So we know there must be 4 zeros in the complex plane, but now I can do better. I can say where, at what distance at the origin, maximal distance at the origin, they all must be. They may be on the smaller distances, but they definitely need to be in some circle of the radius r. And I can establish the condition where they lie. So how can we establish the condition? What is the function f and what is the function g for this case?
Well, f of z is set to the 4.
F of z is z to the power 4, and g of z.
Will be the remainder, z squared plus 1.
So how do I know what radius should I choose? What should I demand?
Z to the 4th is greater than
Z squared plus 1. So this is the equation that I need to solve. Okay, so we decided to choose a big circle. So we're saying let it to be r in the power I phi, which parameterizes the circle of the radius r. And then what this equation reads, so what this equation tells us will be r in the power 4 is greater than r in the power 2 if the power 2 I phi plus 1 absolute value. And what this equation tells us is that r into the power 8 is greater than r into the power 4 plus 1 plus 2r squared cosine 2 phi. And this is satisfied if r in the power 8 is greater than r in the power 4 plus 1 plus 2r squared. If this is satisfied, then this condition is satisfied for all phi's. Which means that r must be greater than 1 plus square root of 5 over 2. So it means that all 4 zeros of these polynomials lie in the area somewhere inside the circle of the radius 1 plus square root of 5 over 2. No roots are allowed to lie outside of this area on the complex plane. And I know it without solving this equation. Okay?
So how do you find the R?
So I had this condition. And then I just can solve this equation, yeah? I can call r square a new function, I don't know, x, and solve it, yeah? Well, okay, let's solve it together. So this thing is r in the power 8 is greater than r in the power 2 plus 1 square. Correct? So it means that r in the power 4, everything is positive, is greater than r squared plus 1. So it means that r in the power 2 minus r squared minus 1 is greater than 0. And then I denote and I solve it. But the entire point is just to show how we get a bound on this function. Okay. So that was a statement about Roche theorem, and now I'm going to switch a little bit gears and discuss the next concept, which is pretty much related to the concept before, and it's called Riemann sphere. And we'll be spending the next few lectures on this concept. Okay. So let me explain you the idea. So we were talking about a complex plane so far, which means there was a set of points with real and imaginary parts, and Riemann came with a brilliant idea to look at the complex plane from a different perspective. he suggested to look on the complex plane as a sphere. So when we talk about complex numbers, there's always a special number that pops up many times, and this is infinity. This happens many times when we need to divide some finite number by 0, then we say they're getting something at infinity. Now, infinity in our calculation was never defined. It was just an abstract thing that something is very large and we cannot define it and we cannot use it for our calculation. And this is how the idea of infinity usually happens in mathematical analysis. But Riemann understood that infinity can be treated as any other point, that it's not a special point. So essentially, he decided to augment a complex plane and add to it one additional point, which is called an infinity. So it's an augmented construction, which is equivalent to the complex plane plus one more point, which is called an infinity. So mathematically speaking, if C denotes our usual complex plane, then there is one more point that is brought to it, and then there is a construction which is called C and infinity. And this augmented complex plane, it's sometimes called Riemann sphere. And the usual, I'll forget. Now, so let me construct a Riemann sphere geometrically, and I'm gonna do it using thing which is called stereographic projection. So how many of you ever heard about stereographic projection? Did any of you ever heard about stereographic projection? Well, okay, so stereographic projection is a very, very old construction that was known to ancient mathematicians. It was known to mathematicians in ancient Egypt and Greece, and people like Ptolemy knew about it. So it's one of the oldest way to understand the geometry. It's called projective geometry, and this is the way to think about geometry. Is the favorite way of ancient Greek mathematicians. So let me explain you the idea of projective geometry and stereographic projection. So let me start with two-dimensional version. Of stereographic projection, because it's easier for me to draw objects that are two-dimensional rather than three-dimensional. But it's essentially the same idea. So I will draw an example of two-dimensional stereographic projection, and for this I need to draw a circle, and it can be any circle. This is the best that works as a circle. And then there is a point on the top of the circle, and I will call this the point on the top of the circle. I will call a North Pole. And now I'm going to construct a stereographic projections of the points on the circle onto the real axis. So it will be projection of the point P on the circle onto point P prime on the real axis. And how do I define it? Okay, let me take a point. This will be point P on the unit circle. And how do I project it on the real axis? Very simple. I draw a line, a straight line from northern pole to the point P. And the point where it crosses the real axis will be called point P prime. It's a projection of a point P on the real axis. Let's see if you got the idea. What will be the projection on the real axis of this point? It must be a point. The point itself. I draw the line from here to there. It crosses the real axis at this very point. That's the point. So this point is projected to itself. Okay. Now let me choose a point. Oops. Right. Let me now choose another point. Let me choose a point here. And I'm drawing it projection. So this point will be projected somewhere on a very large positive number on the real axis. So the conclusion that we draw from this analysis, from this geometrical analysis, that all points in the southern hemisphere, so to say, are projected inside the well, if these are points r and minus r, if the circle is the radius r, then these points will be inside the segment minus rr, and the points in the northern hemisphere will be projected outside. So as close as I come to the northern pole, the further away is the projection point. And finally, when I come very precisely at the north pole, where will I be projected? Infinity. Yes. So now I don't know what I mean when I say infinity on the real axis. But when I look at the circle, the point which is called northern pole is not any different from any other points. So now when I added this special point, which I call infinity, and I look at the circle, then including northern pole, then everything is fine. I've constructed a one-to-one mapping between the infinite line and the circle. And this mapping is called stereographic projection. Very powerful geometric construction, known for centuries. Now we're gonna do exactly the same construction, but in 3 dimensions. Just a second. The only difference is it will be harder for me to draw. Yes. Yes, for here, the point infinity is a unique thing. There is no distinction between plus and minus infinity. All points at infinity are identified and considered a single point, which is infinity. Thank you. It's a very, very time equation. So there is all finite points are finite, but there is one point at infinity, and it's added to the line. Okay, so now I'm doing exactly the same construction in 3D, and help me God to draw it. Yeah, just a second. Okay, so this is okay. So far, so good. Then I'm drawing a sphere. Well, no, okay, enough. Attempt number 2. Okay, let's say that's a reasonable sphere. So this is point 1, This is point will be I. This will be point. Sorry, somewhere there will be point. Nope. Well, so just okay, better. So here I draw so this will be point minus I, this will be point. So, okay, so this is the sphere, this is the northern pole, there is a southern pole, and at the equatorial line, I placed a plane and I identified this plane as a complex plane. So X and Y axis of this equatorial plane are real and imaginary part. Okay, and let me draw a sphere of the radius 1. So it means that the projection, sorry, that means that the cross section by the complex plane will be a unit circle. So this will be the point 1, this will be the point minus 1, this will be the point I, and this will be the point minus Y. So this was just a drawing of a sphere, three-dimensional sphere, which has a mathematical description: x squared plus y squared plus z squared equal 1 on a complex plane. So what are the coordinates of the northern pole? Just to make sure that we understand what are the coordinates of the northern pole in this reference frame. 0, 0, 1. So this will be axis x, this will be axis y, this will be axis z. What are the coordinates of the southern pole? 0, 0, minus 1. Correct. And complex plane lies in the plane z equals 0. This is the complex plane. So the cross section of the unit sphere with the complex plane will be x squared plus y squared plus z squared, which is 0, is equal to 1. This is geometrically a description of the unit circle. Okay, and now I'm gonna do a stereographic projection, but this time using a three-dimensional sphere, well, a two-dimensional sphere embedded in three-dimensional world instead of a circle. So what I'm gonna do, I'm gonna project a point on a sphere to the point on the plane, or vice versa, whatever you choose to look at it. So how do I do it? I pick a point on a sphere. Let's call this point P. And I draw a line that starts at the northern pole and goes to the point P. And somewhere this line crosses the complex plane. And as you see, for the southern hemisphere, it happens within the unit circle. So somewhere will be a point P prime that lies on the complex plane. So what we have accomplished, we have accomplished a mapping between the point on the complex plane and a point on the sphere. Did you understand it? If you understand, let me ask you a question. You have a question? Where on the sphere lies the point of the origin?
On the southern hemisphere or south?
On the southern pole.
The south pole.
So if you draw the line that starts at the south pole, it will go through the. Oh, that was an attempt to draw a straight line on iPad. Okay. Now, what we see from here, that all points on the south in the southern hemisphere are mapped into the interior inside the unit circle. Inside the unit circle. So what about points in the northern hemisphere? Where are they mapped? If I now take a point in the northern hemisphere, where will it go?
Outside of the sphere.
Correct, outside of the unit circle. It will go somewhere there. And once again, the closer I come to the northern pole, the further away from the origin on the complex plane the point will be. And therefore, I can call the northern pole the point at infinity. So any finite point on the complex plane will be somewhere on the sphere except the northern pole. And northern pole itself will be at infinity. So, and Riemann's suggestion was, let us consider the manifold, which is called Riemann sphere after him, which is mathematically identical to the complex plane with one point added to it, and it's called the point infinity. But now point infinity is properly defined. It's just a point on this manifold. It's a northern pole. So all finite points on the sphere except northern pole have one-to-one correspondence to the complex plane, and there is one point, special point, which was not on the complex plane. It's a northern pole itself, and this is added. This is one point added to the complex plane. That's the mathematical construction, which is called Riemann sphere. Let us discuss some simple example.
So does that mean the projection of south is the north pole, which is also infinity and minus infinity?
No, I didn't like the beginning of your question. The projection of the south pole is an origin. So you draw the line from northern pole to the south pole, and it crosses the complex plane at the origin. So southern pole corresponds to the point z equal 0 on the complex plane. This is this line. It crosses it here. So there is a correspondence between point at the origin and the southern pole. So point z equals 0 on the complex plane is mapped to the southern pole on the Riemann surface. There was some question in the chat. What is the chat? נמצא z equal minus 1 בכל מקום אמרנו שוב הקוטב הדרומי. אז z 0 עכשיו הוא ב...
זה בגלל שבזום זה הופך את האנגלית, אז רשום פה, אבל מקודם אמרנו שהקוטב הדרומי נמצא בזה equals minus 1. אז עכשיו הוא בזה שווה ל-0. הכוונה היא שהפרוג'קשן שלו נמצא ב...
Sorry, it's a confusion. So there is a... Sorry, I should be more careful. Thank you. So there are axes x, y, and z. X, y, and z. These are three-dimensional axes, and I got confused between the axis z and the complex number and the standard notation for the complex number z. Sorry. So okay, so let's try to focus on now then I erase this equation. Now point, so complex plane as a plane is at the coordinate z, three-dimensional coordinate z. Now this is a complex plane. So the problem is, yeah, so defined x, y, and z, and this is extremely easy. So on a complex plane, the numbers are x plus iy. These are numbers on the complex plane. On the complex plane. Yeah. Okay, sorry. Okay, so numbers on the complex plane are x plus iy. Now the number 0 plus I0 on the complex plane. Which we normally call the origin of the complex plane. This is this point. The entire complex plane is this construction. And it lies at the value z equals 0, at the value of three-dimensional axis z equals 0. And it's being mapped to the southern pole by drawing a straight line from the northern pole to the southern pole. And this thing crosses the plane at the origin. So this is the value x, this is the value y, and this point corresponds to x being 0 and y being 0. Therefore, southern pole is being mapped onto the x and y being 0 at the center, so to say, of the complex plane. I hope this resolves the confusion. Okay, I'm sorry, I'm using z as a standard notation for complex variable, and I just a minute ago used that as for the axis.
So the North Pole, I'm sorry, if we project a point on the complex plane, I'm sorry, on the northern hemisphere, and we want to reach the North Pole, it doesn't matter if we're coming from x as we go over to infinity, we can go on the y-axis, on the imaginary axis, and we go to infinity. Like,
It doesn't matter. Any point, the further is the point from the origin, the closer it will be to the northern pole. Am I answering?
so okay, so like there's a huge, it's like an infinity.
Yes. So you can think there's a circle that circles near the northern pole, and points on this circle will correspond to some huge circle on the complex plane, and the smaller you choose the circle near the northern pole, the bigger is the radius of this circle on the complex plane.
Yes, so the actual points north will correspond to an infinitely large.
So the point of northern pole, so all points on the infinitely large circle are identified and they consider to be the same point. So that's the construction. So you're allowed to have a circle of any finite radius, and there is a one extra point added to the complex plane. This is the points of infinite radius, and all points on this infinitely radius circle identified, they consider to be the same point. So it does not make, within the Riemann construction, within the Riemann hemisphere, within the Riemann sphere, it makes no sense to talk about different points on the infinite circle. They all are the same point. They identify as a point infinity. So all points at infinity, so to speak, are one point, and they being glued to the northern pole. Okay. So let us see what is the advantage of so far we have defined a construction, we called it a Riemann sphere. Now we need to see what are the advantages of this construction, what it allows us to understand that was previously unknown. Let's discuss a function f of z, which is a ratio of two polynomials, g of z and h of z. G of z and h of z are polynomials. For example, let's consider some very simple example. Let's consider function f of z, which is z minus 3 divided by z plus y, z plus I. What could we say about this function on the complex plane if we're interested in its analytic structure?
As far as zeros and poles go,
Correct.
one pole of order 2 and 1 0.
No. Two poles of order 1 and 1 0. So 0 of f of z is at the point z equals 3, and poles of the order 1 at z equal plus minus I.
They're both plus.
Yeah, you probably meant.
Oh, I'm sorry. Sorry, my mistake. Yeah, sure. Everybody is right. Sec. So this must be a minus. Now, let us see what this function does for the points on the Riemann sphere. Just so now it's a Riemann sphere, not a complex plane. And this function maps, if previously it was a mapping from complex plane to complex plane. Now it's a mapping from Riemann sphere to Riemann sphere. So what can we say about this function as a function on the Riemann sphere? They have changed the manifold, yeah? So now the manifold is not the complex plane, manifold is a Riemann sphere. And I'm mapping the function from one Riemann sphere onto another Riemann sphere. So if previously point I plus minus I was point of pole, where's the point, where the point is equal I and minus I am mapped now?
To the point at infinity.
Which is the northern pole. So these two points are now mapped. Let me use another color. So now this point is simply a point that is mapped onto the point on the northern pole. And this point is also the point which is mapped on the northern pole. Well, and all other points are mapped somewhere. So it's now a mapping from one sphere onto another sphere, but on the Riemann sphere, now the function is completely analytic. This mapping is fully defined. There is no point of singularity whatsoever. We now have a function from one sphere onto another sphere as in a function on the sphere to another sphere. It's a completely analytic function everywhere. Now, that was a very simple example. Let me consider slightly more complicated example. Let me consider function, maybe not more complicated example. Let me now consider function 1 over z. Once again, we can repeat the same story, you know. On the complex plane, this is the function that has a pole. Where does it have a pole?
The origin.
At the origin has a pole z equals 0. It's the pole of degree 1. We all know what to do with this thing. Now let us see what this function does with a Riemann sphere. Okay, I have to draw one Riemann sphere one more time. I think by the end of this course, I'll be very good at drawing spheres on iPad. You see, I'm getting better. 1 I minus I minus 1. This is my original sphere. This is my original Riemann sphere. This is my Riemann sphere where the point z lives. This is the counterpart of my original complex plane z. So that was my complex plane z. Now it became a Riemann sphere z. Now function 1 over z is a mapping from this complex plane onto another complex plane, or better to say it's now a mapping to another Riemann sphere. And I'm drawing another sphere. That's a new Riemann sphere. That's a new. And now, what can I say? What can I say? What does this function do? Where the point z equal 1 goes?
To 1, the same.
So z equal 1 goes to itself, to z equal 1. Well, I was slightly not accurate with x, but I think that the drawing is clear. Point z equal minus 1. Point z equal minus 1. Where does it go?
The same point.
It also goes to the same point.
So
Where goes?
The southern pole now become the northern pole. So it's flipping the sphere.
The southern pole becomes the northern pole. The northern pole becomes, what about the northern pole? Where the northern pole goes?
To the southern.
To the southern pole. So they exchange. So now, so look at this and now tell me what happened to any point on the Riemann sphere under this transformation. What happens to any point? What happens to the sphere?
Just flipped.
No, surface is not split. The sphere is not split.
לא, כי נגיד I הולך למינוס I, מתהפך.
Okay, so what do I do with this? So if it's a ball, what do I do with this ball? Imagine you have a ball.
You spin it.
I turn it with respect to what axis?
On
There is an axis of rotation. I'm rotated around some axis.
the X,
The x-axis, and by how much?
180 degrees.
Yes, so it's a rotation by pi with respect to the real axis, which we called x. So this transformation, it was doing something on the complex plane, no question about it. But we can also understand geometrically. We can also understand geometrically what it does to any point on the Riemann sphere. It just rotates Riemann sphere by pi. And the geometric meaning of this is pretty clear. And we also, because our mind thinks geometrically, we can immediately say some things about this without thinking twice. For example, if we know that on the original sphere what two lines that were crossing with some fixed angles, that after this rotation the angle does not change. Correct? That's obvious. If we have a ball, soccer ball, yeah, with some pattern on it, the ball rotates, the angles on this pattern don't change. So this immediately obvious from geometric interpretation of this, and such transformation, they're called conformal mapping. Conformal transformation do not change the angles. And such transformation, they correspond to a rotation of a Riemann sphere. So we consider a very particular transformation here. We have considered a rotation by Riemann sphere by 180 degrees with respect to x-axis. But in fact, understand that we can take this ball and rotate as many times as we want. This will not change any angles between any lines on the sphere. So there are many ways to rotate this ball. So they all constitute a family of transformation, which is called conformal mappings, conformal transformation. They all can be think and represented as a rotation of a Riemann sphere. So this is one immediate advantage of this way of thinking. Another way of thinking is now is the singularity of the functions at infinity. You remember we had many cases when we have a function which was singular at infinity. But we did not have a good way to analyze the singularity at infinity because infinity was always very special, right? How to treat infinity, it was not clear. But now infinity is just a point on the Riemann surface, just a point like any other point. So now we know how to analyze singularities at infinity the same way we did for singularities at any other point. We will discuss it later in more details. So these are immediate advantages of a Riemann sphere. Okay, guys, I think it's time for me to stop. So if you have any questions so far.
If you could just explain the mapping of the points, because I guess I missed something.
Okay, let's go.
You said the function is 1 over z.
Correct.
Right, so I just plug
You plug I, it goes.
Divide and multiply by I to get I to the top, and I get minus I.
Correct.
And that's how you.
Yes.
That's how you understood that the North Pole goes to the South Pole. Like I just don't understand that.
So southern pole is a point at infinity. If you divide 1 by infinity, you get 0. But 0 is a southern pole. So we started with the northern pole. Northern pole was infinity. 1 over infinity is 0. 0 is a southern pole. So you have 1 over z. You have 1 over z. Let's take z equal infinity. Now infinity has a very well-defined meaning. So 1 over infinity is 0. 0 is in the sense of complex number. So it's 0 plus I0. This is a southern pole. Sorry, this is the southern pole.
This is where the Southern Pole
Yes.
gets projected.
Gets projected. So we started with something that was on the northern pole, and it got projected to the point which we know corresponds to the southern pole.
I would just like, so infinity is in the Northern Pole on the west.
Okay, so let's say points on the complex plane. Point 0 plus I0 corresponds to the southern pole. Point which is schematically denoted as infinity corresponds to the northern pole. Agreed?
They get mapped to that.
Okay, so there is one-to-one mapping. Yes, they get mapped there. Now, under the transformation, 1 over z, the point infinity becomes point 0 plus I0. Which corresponds to the southern pole. And this pole, infinity, was at the beginning northern pole. So northern pole and southern pole flip.
But I can see a point now that we can have multiple Southern Poles.
No, we have only one point on the sphere which is a southern pole, and one point which is called northern pole.
But what if we take a certain polynomial instead of 1 over z, 1 over some sort of z polynomial?
Right. Right. So that will be roughly speaking our next subject. Okay, but in a very broad sense, that will be and we will go from Riemann sphere to Riemann surface. And that will be our next natural construction. I don't know how much time we will want to spend on that, but that's what is called Riemann surfaces. And for any function of complex, any analytic function of complex analysis, there is a Riemann surface that corresponds to it. Okay, people. Any more questions? Okay, then stop here.